source code and object code coverage for safety critical systems. As you've seen, few words about me. Martin Heininger, Managing Director of Heicon Global Engineering. About 20 years of experience in aerospace projects. So that's the huge amount of my professional life, actually, I spent in aerospace. In the last 10 to 15 years, I also did automotive projects, railway projects, industrial automation projects. In the topics, as they are mentioned below, requirement engineering, test engineering, and management of functional safety. And it's hands-on coaching, what you get from Heicon. So the topics we are doing the consulting, we have experience, practical experience in it, and we deliver solutions which are usable in your projects. Yeah, and these topics, requirement, test, and management of functional safety, the topic of today fits very, very well into these areas, in all of them, actually, almost. Structural source code coverage measurement. When we start, or before the first topic, what we are doing is the structural coverage. I will show you the structural coverage in opposite to the functional coverage. Probably most of you are aware of it. And then I will talk about a research project which we have done in the last 2 years, the COCOSI, the German-funded research project, where it was investigated actually how much benefit could you get from measuring the source code coverage on system, embedded system, an integration level instead of doing it on unit test level. So running the software and the real hardware and measuring the code coverage. As up to now, the instrumentation of the source code always caused in a lot of projects quite a number of troubles actually. And the non-instrumented code coverage, so on object code level, could for the future solve these kind of issues, this instrumentation, or it solves the instrumentation issue for sure. And there is no impact on runtime and memory, additional memory needed. So it was an idea to say, let's have a look from a research point of view, how much benefit could we get in such project if we do it that way, what would happen? And that was possible because the technology to measure the code coverage non-intrusive, there are several companies now on the market who do provide such solutions. And this was the starting point of the research project. So in conclusion is then the handover to Ingo, who will go a bit more into the instrumented source code coverage measured by vectorcast, and Matthias from iSystem will show you then the non-instrumented versions and compare it actually both together, and then we have the Q&A. Okay, let us start with the comparison or what is structural coverage, what we are talking about here, and I put it onto the slide in that way. Structural source code coverage, as if you buy a test book, in any test book you get white box testing, and white box testing more or less means looking into the source code, therefore white box, so open your box, yeah, look into it, what is there, and in our case it's software. So we see it in the source code, and the criteria for testing is the source code lines or conditions, yeah, as here, if A and or B and C, there are criteria there. I can say what has to, when is this condition here complete, modified condition decision coverage as a term here, or lines of source code or branch coverage. So these are the 3 typical ones which are on the market. So that is what structural coverage testing is about, or is focusing on, actually, on covering the source code. In opposite, almost, I would say, to that is the functional testing, yeah, where you have the your unit under test is closed, your box is closed, yeah, your system is you don't know what the software is doing there. You have no visibility on the software. You just have external inputs and outputs, and you have functional requirements like here. The heating control unit shall set the output signal vent 2 to 5 volt 2 minutes after the temperature has fallen below 5 degrees Celsius. So that's obviously some embedded system, and there is some input signal the output signal went to, which drives some further mechanics, and there's a temperature measurement as an input to our system, and our system compares actually measures the temperature, and if it is below 5 degrees, then it starts acting. So this is completely out of scope of this webinar here, this kind of testing, but it's very, very important. And let me go one step back actually in the history, or let us make a step back. The aerospace industry has started with its with a software standard DO-178 in the 80s already. Yeah, so the key, we want to develop software even for safety critical systems. So we need to define a standard, or we need to define rules. And even at that time, the following thoughts were made. We have, or we will request requirements, first of all. We need to specify our software using natural language textual requirements at that time, at least. Yeah. So these requirements are strong, very strong in describing functionality. It's up to today still the case. Yeah. But it's natural language, first of all, and secondly, it's overall very difficult to say when do you have described the system completely, yeah, when it is finished. So that's a bit of the weakness of requirements. Then definitely we need dynamic testing. Dynamic testing is very strong in testing functionality and in improving that the functionality is correctly implemented actually according to the requirements. But again, complete testing of a software is not possible. Yeah, all combinations of a software system, if it's a bit more complex, there's no way to test all combinations. So when to stop the completeness is also there, also at the testing side, a difficult topic. There's a saying, if the money is over and time is over, then test stops. Yeah, but this is not good enough. And then they thought, or the idea came up, structural coverage, if we could measure them, this would be different. Because structural coverage is based on the source code, as we have seen before. Yeah, if statements covered, or decisions made, or lines of code covered, and the source code is mathematically based on mathematics, and therefore it's actually also the coverage can be expressed in mathematical expressions. So it is 100% clear or defined what is 100% statement coverage, 100% MCDC, 100% branch coverage. There's no debate about it. So where structural coverage is very weak and very bad, actually, not only weak, it's just not possible to test functionality by looking into structural coverage. As there's very little points in the MCDC, you can argue a little bit about functionality, but 99% is only about completeness. Therefore, structural coverage is there. And if you see here this diagram now, or this plus and minus, you see there is a complement. Yeah, the structural coverage is the complement of the requirements of the dynamic testing, and therefore this was the idea. We want to have the structural coverage. We will request the measurement of structural coverage already in the very early phases. So after that, tools were developed and ideas were developed. How can we measure the source code coverage? And it came up that the only possibility at the time, the 80s, 90s, 2000 years, the only possibility is to instrument the source code, so to change the source code. Ingo will tell you a little bit more details about it, how and what to do there. I stay more on the high level here. Overall, the instrumentation changed the runtime behavior of the system. no doubt about it. And in an embedded system, this can lead to the fact that the system may not work anymore. If you instrument the full software and run it on the embedded system, it may be, due to the functionality of the system, it may be the case that it's just going always in error state, or it's not even coming up or something like that. So this was, for a long period of time, the difficulty. And there were the conclusion, it's not possible, or we're not doing it. We're doing the code coverage measurement on unit test level, yeah, because there we have no problem. On unit test level, we have 1, 2, 3, 4, 5 functions, at least not many. And even if we execute them on the target on our processor, there is enough space and enough place to measure the coverage, and we do not care about any timings. Actually, the unit testing is completely decoupled from any time measurements or any performance stuff. It's logic, and there we measure the coverage, and that's how it came to the fact that the unit testing is the testing a level where we're going to measure the structural coverage. The big disadvantage here is this functionality, that on unit level, it's the biggest, there's the less requirements. Yeah, you do not have much of functionality described on a unit test level. Okay, aerospace industry has 3 levels of requirement: high level, low level software requirements in textual form. But even with that, low level requirements are still describing a lot of details of the implementation, but not how overall the system works by nature. Yeah, therefore they are low level requirements. So this was the weakness. So this idea because the idea was originally is the functionality completely described in the requirements, and this was difficult with unit testing all the decades or the years since we're doing it. And this was the starting point for this COCOSI research project. Here, with the non-intrusive code coverage method, we could move the structural coverage measurement to the system and integration level, yeah, because we have no impact anymore on the runtime behavior. We have we do not need more space for the source code. So even on small targets, this could or will work, and then we would fulfill this, let's say, dream some decades ago, that we really can check the code coverage, the completeness of our requirements and our tests on system and integration level. Due to the limited time, I can't discuss now the details of the research project. I just bring here a summary. Details about the technology you will get by Ingo and by Matthias in a few minutes. One of our results is that it is quite likely and possible even on the real-time conditions or real project conditions, that you get a coverage of 70% statement or even MCDC. Yeah, this is not really depending on MCDC or a statement. 70% source code coverage on system level. This is really realistic, and that's good news, because this means that it makes sense to think further about it. Yeah, because if it would have been only 30, 40% or less, or 50% and not more, then it's really questionable whether it makes even any sense, because coverage measurement means actually completeness. You would like to have in the end a statement about 100%. Yeah, so this means you have to analyze, or you have to act somehow on this remaining 30%. And I missed one point. The 70% is true if you do fault injection testing. This is, of course, let's say in a safety system, kind of obvious, but yeah, not to forget. Next point was to obtain a meaningful statement from the coverage measurement. You need a strict coupling between the test execution and the coverage measurement, because otherwise, if you switch on your system on the hardware, it's idling and it's polling certain interfaces and doing some stuff, and you get 20%, 30% code coverage by doing nothing, just switching on the system. And that's, of course, not acceptable for any safety project. Yeah, we need a clear coupling that the coverage is detected by the test and by nothing else. But this is possible, means we have to have an interface to our Hill systems, the coverage measurement tool, but it's all feasible, at least due to our research results. This leads to the fact that the unit testing can be a bit relieved from formal requirements. We are not saying we don't need any unit test anymore. That's not the statement. It's doing about traceability requirements to unit testing was always a pain, or is a pain, and is problematic. taking other people than the developer, forcing them to write unit testing, cause a lot of questions and issues in the project. Yeah. So if we can do the code coverage on this level and we fulfill also the other constraints, then we believe that unit testing can get a bit more back to the software developer where it should have been all of the time. Yeah. But in the last 30 years, we needed the unit test formalized to have code coverage measurement and to have traceability. Otherwise, we can't prove the necessary things. What is also a result is if you look onto model-based development, there are developments there where we are going to limit the number of textual requirements or the levels of textual requirements to only one in ideal cases. Yeah, we may have in future only one level of functional requirements, textual functional requirements, and the rest is in the model. And if we can do on this level, on this is the high level, the system level, yeah, if we can measure their code coverage, this will be very beneficial, yeah, and support even the model-based development. So some more results. There are scenarios which limit the possibility on system level, and as it was a research project, we had the time to investigate here a little bit, and the results are there. Of course, the economic efficiency of the test environments limits actually to get full coverage or something like that, because this fault injection testing, for example, is expensive. Yeah, performance testing can be quite expensive to do some edge cases. Yeah, the test environment gets really, really expansionally expensive. Then risk for test personnel, actually, if you run rotating motors, for example, rotating parts, yeah, this can be very, very dangerous. Therefore, it's not allowed and has to be stopped. Or gas, for example, yeah, measurement of high concentrations of some gas, which is not easy to handle. These are projects which we had a look into. Robustness of development of the developed software, of course, is also an point, and there's the most known is the defense programming. Yeah. Then the source code readability. Sometimes you put source code parts there where you put just some information there. It's more for readability, or some code parts is for readability, but it causes problems in the code coverage, at least on the integrated, on a fully integrated system. And some, of course, mechanically locked combinations of sensor values, yeah, high speed and extreme steering, Angel, for example, yeah, are not possible. Again, kind of fault injection. So this limits then the system on system level. However, our example in the research project delivered 74% branch coverage, and this was achieved even by having a source code really drilled down to get examples, yeah, to deliver worst case value scenarios, yeah, to get really bad coverage, yeah, because the idea was, okay, where are the real problems? So we forced our system to make it quite difficult, but even there we could achieve a 74% branch coverage. Branch coverage, but not MCDC. And MCDC is currently in work and will be actually outside of this project, out of research project. It will not be implemented. Actually, there are some limits. This will go beyond the research project, and we had some limitations in our industrial project due to Corona, and therefore we couldn't complete everything. But Leaper was our partner, our industrial partner there, and we had some support from them. And it's some part of the statements I made there is coming from this area. And there is an analysis required, or we need further investigation are needed actually for the newly object code-based coverage gaps. Yeah, this is currently under work. Project will end of October. Then there will be a report available, such as overall object code-based coverage gaps, such as limit checks or additional jumps conditions due to code optimization. There are some new challenges in coverage if you really want to do it 100%. It's not surprisingly, but it's manageable, but it's there and has to be considered. Okay, so my 15 minutes are now almost done. The conclusion here is both is needed. Even we investigated now the non-intrusive code coverage systems. Yeah, it definitely supports the requirement engineering through the throughout the completeness check. Yeah, it identifies missing test cases. Yeah. It strengthens the integration and system test compared to the unit test. Yeah, as it forces them, you suddenly can make statements about quality of your system tests. Yeah, due to the coverage measurement, just a number. Yeah, what is your coverage, your structural source code coverage? Then you, with some experience, you can make a statement how good your systems tests are. MCDC is not there and will be definitely not coming up as fast as possible. And some aspects you have seen before, which limits the, we need to collect experience with the non-intrusive code coverage systems. Yeah, the instrumented source code coverage is known since 30 years. So there's all things are known, all questions from authorities are solved now. Yeah, as you will see in a second from Ingo. So my last slide here, the sponsorship of this research project. First of all, the partners were Intel, Germany, Axemic Technology in Kiefersfelden, Heicon and Fraunhofer, Kaiserslautern from a research point of view. And the funding code is here of the research project. And yeah, you're welcome to discuss further on this topic and to follow this webinar. And that was it from my side. Ingo will give you now an insight to the instrumented source code coverage and the possibilities, the well-known possibilities with this tool since 30 years. Yeah, some of them. But he also will present you some new things. Actually, it's not only past. Ingo, your stage.
I will try my very best. Thank you. Hello, welcome. My name is Ingo Niklas. I'm field application engineer. I work for Vector for 10 years now. And I did software development before, so I've even 20 years of software development before, so I know the business of developing and testing software from both sides, from developer side and from tool vendor side. Vector is offering tools for all phases of testing, and I show on this slide I show the different kinds of testing that you can do, starting with static code analyze, where we are just statically analyzing the source code. We recently bought PC-Lint, so it's now part of our portfolio, part of our products. So for static code analysis, we also have a tool now available. For unit testing, if you just want to test a small piece of code, then there is VectorCast for testing functions or function interaction, software integration testing. If we go to higher levels of testing of dynamic software verification, if you want to test software in a loop, for example, then there would be Canoe that can help. And if you go to even higher levels, having the full system integrated, then Canoe and together with BT system can help. So if you're looking for any help in these areas of testing, feel free to look at vector.com/testing. And so the topic of today is code coverage measurement, and code coverage means we want to see, or structural coverage, we want to see which lines of code were executed, or which object code was executed when dynamically executing the source code. So this is the area where we have experience with VectorCast, and we do measure the code coverage with source code instrumentation. And it's true that there are some benefits from instrumenting the source code, but there are also some drawbacks. So it's let's first look at details again. I mean, Martin already showed a little bit of how this instrumentation can look like. So on this example code that I stole from Martin, I just added these 3 instrumentation points so that you get an idea of well, even how complicated it can be. So if we look at this code, there are no curly braces around the code under test. But if you add instrumentation points, you need to have these curly braces, because otherwise this will probably result in problems when running the code. or even compiling the code. So in the end, you will get a report that says which line of code was executed or not executed. So why is coverage measurement with source code instrumentation still out there and so successful? Well, it's the best practice for many years. We are out with the Vectorcast for more than 30 years, and it is well accepted in all industries. You get reliable traceability for all levels of coverage, including MCDC coverage, which is difficult from object code, and it works for, well, I would think it. I've not seen a compiler or a chip where we were not able to help. So I said almost all compilers and chips, but that's just because I'm a technical person, and there will probably be some examples out there where it doesn't work, but I've not seen any yet. And the way we measure code coverage with source code instrumentation, we do not require a trace pod. We do not require a debugger connection. We can transport the coverage in other ways if necessary. But yes, there are contrasts. There are drawbacks of this solution. One of the drawbacks is that we have an increase of runtime and an increase of code size, which is obvious. If we have additional statements in the code, then the execution takes time, and also the implementation needs space, and that's why you will have a bigger binary with the instrumented version of code. Also, some of the optimizations are not possible anymore, and that's why you will also have an increase of code size of the binary. And then the last drawback is it may change the functional behavior of the code under test, which is terrible. If you change source code and you get wrong results from your testing, then this is not what you want. This is, of course, not what we expect, because usually the instrumentation will not change the behavior. But to be perfectly sure, you need to rerun all your test cases with the uninstrumented version. And this is exactly how we can help with relieving the pain, how we can help with addressing the drawbacks of the coverage that is measured by instrumentation. We implemented in the last 30 years a couple of improvements regarding runtime, regarding code size. For example, and this is a thing that we had, I think, even in the first version of Vectorcast, that we only use 1 bit in memory for each instrumentation point. And while the test executes, we do not write out any information. We do not print anything, because this would be too time consuming. We keep the bits in memory, and we wait for a better time to read the instrumentation, to read the coverage from the board. We have 2 different options how these instrumentation points look like. We can use bit shift operations, or we can use function calls. And both have advantages or disadvantages. The bit shift operation is quicker because when calling a function for each instrumentation point, this means at runtime all registers need to be pushed to the stack and then popped from the stack again, and this for each instrumentation point. So this takes time. But on the other hand, I believe that the bit shift operation takes more implementation space. That means the binary is getting bigger. So depending on where you have the most problems, you might choose the one or the other option. In most cases, it will be recommended to use a block mode coverage. If you have, for example, a block of statements where you do not jump into or out of it, and then we only add 1 instrumentation point at the end of the block if you enable the block instrumentation. And this, of course, means that if this instrumentation point is hit, then we have executed all statements inside that block. When it comes to code size increase, then the code size increase can be a real problem. So I've heard a number of, for example, 40% of code size increase. The binary is getting 40% bigger, which can be a problem on some devices, or in many cases, you will have some, let's say, 10 or 20% of spare place available. But maybe not 40. And if you go to MCDC coverage measurement, then it may be far more. And this can be addressed, for example, with partial instrumentation, which means do not instrument all files, just instrument parts of your code. And then, so if you instrument the first quarter and the second quarter and the third quarter and the fourth quarter of your software, then you need to rerun the same test cases 4 times, which different parts of your software instrumented. And then in the end, we will aggregate the coverage from these 4 executions and show the overall coverage on all source code. Also, we help with this partial instrumentation. We have a Python script integrated into the Vectorcast cover tool. And if I have time, I will show at least the Python script in the end of my part. Also, what is important is that it depends what kind of code coverage you want to measure. Do you want to measure MCDC coverage, or do you want to measure maybe just function coverage? Because for function coverage, all you need to have is one instrumentation point at the beginning of every function. If you want to measure MCDC coverage, you need far more instrumentation points, obviously. And for example, in ISO 26262, in higher levels of testing, system level testing, for example, there is only required function coverage according to ISO 26262, or a function call if you go to higher levels of criticality, but not statement or not MCDC coverage. It's a fact that the instrumentation might affect the functional behavior, and we cannot avoid it. When instrumenting the source code, it might affect the functional behavior. So what you need to do is you need to rerun all test cases with the uninstrumented version of your code. And maybe since you need to rerun them anyways, it might be okay for in your case, in your industry, with the level of criticality of your product, that you can run your fully instrumented software on the bigger brother or bigger sister chip of the chip that you are finally using. Maybe there are multiple chips with more RAM or more flash memory, and then you can run your instrumented versions of the code on the bigger chip. We have an additional benefit that comes from the instrumentation, and that is that for each instrumentation point that we add into the source code, we allow you to do code injections, and you can inject any code that you like that is valid, compilable inside the namespace of the instrumentation point. We also have or offer additional functions, utility functions that you can use to do additional outputs prints. For example, you can print the values of globals or of a tick counter register to check timing or things like that. And the nice thing with these probe prints that we offer is they do not just print to stud it out as a printf function would do, but instead we are printing, well, more or less into the same buffer that we use for the code coverage transfer. And then we use the same transport mechanism that we also use for the code coverage transport. So that means that you can get the logs from the embedded device, the logging from the embedded device with these utility functions. The probe points can also be used to verify bug fixes. If you find, for example, an issue while running your test cases, then you might want to quickly verify with a probe point whether a fix successfully executes the test case. So let me have one quick look, and then I pass over to Matthias. One quick look at the coverage tool. We see on the left side all the files that were instrumented, which is only 4 in my case. And we also see, well, coverage that came from executing test cases. And on source code level, we see the coverage that we achieved. We can see, for example, that this is statement and MCDC coverage. And for MCDC coverage, we also offer a truth table that you can check to see how you should have executed this condition and the subconditions to get 100% of MCDC coverage, or which test cases are missing. So this helps in getting better values of code coverage. I said that to address the code size increase, we offer you a Python script that allows you to measure coverage component-wise. And if you have VectorCast installed, then there is an example environment system testing and system testing example. And the system testing example also has a Python script that supports this component-wise instrumentation. It is commented out at the moment, but if I enable this component-wise coverage, then it enables the multiple execution of the test cases. So this this Python script allows you to let VectorCast control the execution of your system testing. You can define the test cases that you want to run, and you can also define what is a command to run a test case, and then VectorCast will automatically instrument, in this example, component-wise, and then run all test cases, and then we will uninstrument this component and then instrument the next component. And the files for each component are also defined inside this Python script. So if you want to add additional C files, just add them in this part of the Python script. And then when running all test cases, we will update the coverage here, and we will rerun all test cases multiple times and with the name of the component and then the name of the test case. So this is the end of my part of the presentation, and I will now hand over to Matthias, and he will show us something about the non-intrusive code coverage measurement, measuring coverage from the binary. And Matthias, the stage is yours.
So welcome to the third part of this webinar. My name is Matthias Scheidt. I'm a system engineer at iSystem. iSystem is a provider of debugging, tracing, and testing tools for embedded systems. For more information about us and our products, visit isystem.com. This part of the webinar, I want to discuss coverage measurement on the target. The tests are executed directly on the embedded device and not in a simulated environment on the host. This way, it's possible to test the software directly on the target system with the correct architecture while measuring the code coverage. I will point out two methods. First, we will have a look at the instrumentation-based approach, where additional measurement code is added to the existing source code. And second, I will show an on-chip tracing-based approach, where hardware tracing is used to reconstruct the code coverage. We will begin with instrumentation-based coverage measurement. In the instrumentation-based approach, additional instrumentation code is added to the source code so that the coverage should be measured. The additional code is used to check whether specific points in the code have been reached. So let's have a look at this, of course, simplified example. Function is square64 takes an integer input parameter called num. In case the square of num is 64, it returns true, and otherwise it returns false. We add instrumentation points at the function entry, another one in the if branch of the condition, and a third one in the else branch. Now let's assume that the function is executed with a num parameter that differs from 8. The first instrumentation point is executed directly after function entry, so it can be tracked that the function was called. As the parameter differs from 8, the condition will evaluate to false, and therefore the instructions in the else branch will be executed, where instrumentation point 3 tracks that the branch was reached. And this measurement data can be used to calculate the code coverage. The typical flow to get an executable from the source code is that the source code files get compiled into object code files by the compiler. The linker takes these object code files and links them into an executable file. For the instrumentation-based coverage measurement, an additional step, the instrumentation step, is added right before the actual compilation step. Now, the compiler does not compile the original source code, but the instrumented source code for the target architecture. This instrumentation step is performed fully automated by test and coverage measurement tools like VectorCast. In order to measure the code coverage on the target, we can use a debugger for the interaction between VectorCast and the hardware. This slide gives an overview of all the involved artifacts and illustrates the flow, how they interact with each other. The source code for that the coverage should be measured serves as an input for VectorCast. It performs the instrumentation and provides the instrumented source code. VectorCast then triggers the compiler, which is using the instrumented files to generate the binary. And once the binary was created successfully, a Python script is called that automates the execution and result acquisition from the target. The script uses iSystem Connect Python API to control winIDEA. And winIDEA controls the target hardware via a debugger. The binary that was compiled just before is loaded to the target and executed. And as soon as the execution is finished, the resulting measurement data is acquired, goes all the way back through the chain, and is provided back to VectorCast. VectorCast now can calculate and provide the results and reports. Now it's time to see this in action. I will do a short demonstration. On the hardware side, we have a host PC that is connected via an IC 5700 and an IGBT active probe to the debug and trace interface of an Infineon RX TC399XE. This is the active probe, and it allows us to capture trace data at a high bandwidth, which is not required for this demo. The setup is connected to a Windows 10 host PC using VectorCast 2022. We use a unit test environment in VectorCast and winIDEA with the iSystem Connect SDK Python API. Here we see VectorCast. Just let's have a look in the environment details. The execute command uses the execute iSystem batch file, and that basically calls the Python script that I just explained in the presentation. In the coverage menu, we see that the statement and MCDC coverage is initialized. And now I will insert a test case for the square64 function. I had a random number as input parameter num. Let's use 2 as input. And as return value, I expect false, which corresponds to 0. And I add another input parameter, 8. And I expect true, which corresponds to value 1. Now let's execute this test. The binary is generated now. And we see that winIDEA pops up. Binary is loaded to the target, and execution will be started afterward. So winIDEA disappeared, which means the test and measurement data was provided to VectorCast. And in VectorCast, we see that the test passed successfully. And we can have a look at the coverage data. So we see statement and MCDC coverage data. An alternative method to measure coverage is based on on-chip tracing. First, let's have a short introduction into on-chip tracing. An on-chip trace logic allows to track what happens inside the microcontroller at a specific time in detail. The trace logic is configured to generate trace messages for specific events. So there are different types of trace mechanisms. Data trace that can generate events based on memory access. Instrumentation trace that allows to generate trace messages by code writing to specific registers. But the relevant trace mechanism here is program trace. The typical events that generate program flow trace messages are the execution of specific instructions like calls, jumps, returns, and a branch. These trace messages are streamed out of the target device via a so-called trace interface. Since this requires a high bandwidth and an enormous amount of data is produced, the debugger provides a buffer for the trace messages. And in winIDEA, these trace messages are processed and the resulting data is used for profiling, like timing analysis, or coverage reconstruction purposes. Now let's take a look at how tracing can be used for code coverage measurement with the help of an example. On the left side, we see our sample function isSquare64 again. The compiler generates the corresponding assembler code that we see on the right side. We have a multiply instruction. The value 64, which is 14 hex, is loaded into a register. If the result of the multiplication in register D4 is not equal to the value loaded into D15, jump to label 3, which corresponds to the else branch. Otherwise, continue at label 2, which is the if branch. And both branches jump to label 4, where we find the return. With program trace activated, while this function is executed, the following trace messages are recorded. From these trace messages, we can conclude that the function isSquare64 was called. We see the exact same instructions as in the assembler code on the slide before. We see the multiplication, how the value is loaded, and from the jump instruction, we see that the conditional branch that returns 0 or false was executed. Using the debugging information that is part of the binary, it is possible to use the trace messages for a mapping between the assembler code and the source code. This way, it is possible to calculate the code coverage based on trace messages. I also want to do a short demonstration of this. For the demo of the trace-based coverage measurement, we use the same setup as in the demo before. Again, an IC57K with HEBT active probe. This time the active probe is really necessary since we will record trace messages. And this time we will use winIDEA with the focus of the analyzer functionality. For the demo, we switch to winIDEA. Here we see our source code. Function isSquare64. Bottom, we see the analyzer. Left hand, we have the trace area where trace messages are displayed. And here the coverage statistics area. The indicators for the source code are still red since there is no coverage data yet. So let's check the active analyze configuration by clicking the hammer icon. In the options, I just want to ensure that coverage is checked. This looks fine. So everything should be prepared for the coverage analysis. Now I download the binary to the target. This takes a while. Start the analyzer and also start the execution of the target. We see that trace data is recorded. It is visualized directly in the source code. We can see that the else branch was covered, and in the coverage statistics, we see statement coverage of source code lines, object code, condition coverage outcomes, execution counts, and so forth. As last slide of this part, a short summary of coverage measurement with winIDEA. If the target provides on-chip tracing capabilities, winIDEA can be used to measure coverage in a non-intrusive way. No additional runtime overhead is introduced, and no additional code is required to be executed. The original code runs and can be tested. And this is possible up to condition coverage on the target. If more is required, for example, modified condition decision coverage, it can serve as a companion application for instrumentation-based tools. So thanks for your attention. And now I hand over back to the moderation for the Q&A session.